So in this video, we're going to talk about how to determine the inverse of a function from its graph. So what are inverses? Inverses are functions that are opposites of each other. The operations in an inverse function will undo the operations in the original function. This is going to make more sense after we do a few lessons. But to get you started, here's an example. F of x equals x squared and y equals the square root of x are inverses, right? Notice that the square root is the opposite of squaring something, so that's what makes these inverse functions. So what is the relationship between the graph of a function and its inverse? Well, an inverse is the reflection of the graph of a function over the line y equals x. So you can see in this example, this blue function is f of x, the original function. This green function here is the inverse, right? F inverse of x. This orange dotted line represents the line y equals x. So notice that what happens is if I take this original function and reflect it over y equals x, I can actually figure out the graph of the inverse. So now the question is, how do we take a graph and reflect it over the line y equals x? Well, think back to geometry. You learned what happens to the coordinates of a figure when you take it and reflect it over the line y equals x. Well, what happens is when we reflect a coordinate over y equals x, we turn xy into yx, right? We reverse the order of the coordinates. So notice that negative 5, 3, in this triangle here, when it's reflected over y equals x, it becomes 3, negative 5. Okay, this point 0, 6 becomes 6, 0. And this third point right here, this 2, 4, becomes 4, 2. So notice that the order of every coordinate is reversed when we reflect it over the line y equals x. So that's going to be how we figure out inverses given a graph. So if we're given the points x, y on the graph of the original function, we can figure out the points on the inverse by reversing the coordinates. So we're going to use the relation that xy becomes yx. So let's use the graph and table of f of x equals x cubed plus 1 to find and graph the inverse of f of x. So what I'm going to do here is I'm going to take all the x values and I'm going to copy them in my column for y for my inverse. And then I'm going to take all the y values and then make them my x values. So I have negative 7, 1, 2, and 9. So now what I'm going to do on this grid is I'm going to plot each of these points. So I have negative 7, negative 2, 0, negative 1, 1, 0, 2, 1, and 9, 2. Okay, so when I connect these points together, you can see that I can form the graph of my inverse function, right? Notice that it does look like a reflection of my original function. So it's very important to notice here that what we did is we took all the x values and we made them our y values. We took all the y values and made them our x values when we found the inverse. And notice that in fact the inverse and the original function, notice that it does represent a reflection over the graph of the line y equals x, right? So you can see, imagine this is like a mirror right here, and it does represent a reflection. So now you can try this example on your own. Is the graph of the green function an inverse of the graph of the purple function? Please explain why or why not. So you can go ahead and pause the video and think about this question. So what I did to figure this out is I just listed out some points, right? So I looked at the purple function and I just listed out the coordinates of some points. And then I listed out the coordinates of some points on the green function. And notice that the coordinates are reversed, right? So this does represent that relationship that xy becomes yx. So it is an inverse, right? Because it does represent a reflection of the graph over the line y equals x. So let's try this example. Suppose the points negative 2, negative 12, negative 1, negative 5, 0, negative 4, 1, negative 3, 2, 4, and 3, 23 are on the graph of a function. Identify some points that can be found on the graph of the inverse. So we're going to use that same relationship, right? That xy becomes yx. And we're going to use that to figure out points on the graph of the inverse. So we're going to have the points negative 12, negative 2, negative 5, negative 1, negative 4, 0, negative 3, 1, 4, 2, and 23, 3. So these are all points that we can find on the graph of the inverse. So now you can go ahead and think about this question. Create a table to show the inverse of the function represented in table 1, and please explain your reasoning. So go ahead and pause the video and you can think about this question. So what we're going to do to figure out the inverse is we're going to reverse the x and y coordinates, right? So that's what I've done here. So I reversed the x and y coordinates, and that's how I figured out the inverse, right? Because we're going to reflect it over y equals x to find the inverse. And so that means we're going to take xy and turn it into yx. So here's something to think about. We can use this transformation to find points on the inverse, right? That's what we've been doing. xy becomes yx. Well, based on this relationship, how do you think that the domain and range of a function and its inverse are related? Remember that the domain is all possible x values, right? And the range is all possible y values. So what do you think happens when we do this? Well, interestingly enough, the domain of the original function, okay, like the domain of f of x will become the range of its inverse, right? Because x is going to become y. The range of the original function is going to become the domain of its inverse because y is going to become x, okay? So that's what's going to happen here. So all the domain of the original is going to become the range of the inverse. The range of the original is going to become the domain of its inverse. So this is a very important relationship to keep in mind as we work through these problems. So let's try this example. Suppose the domain and range of a function are as follows. So it's all x such that x is greater than or equal to -2. The range is all y such that y is greater than or equal to 0. So what are the domain and range of the inverse? So we don't really need to know any other information to figure this out, right? We can do the domain and range of the inverse because we know that x becomes y and y becomes x. Okay, so when we're talking domain, we're going to talk about the x values, right? So how am I going to figure out the x values of the inverse? Well, I'm going to take the range of the original and make that the domain of the inverse, okay? So I'm going to change my y's to x's. So it's going to be x such that x is greater than or equal to 0, okay? So I just copied exactly what I had in the range, but I switched all my y's to x's. Similar idea with the range, okay? I'm going to go to the domain of the original function and switch all my x's to y's. So this is going to become y such that y is greater than or equal to -2. Okay, so you can use the domain and range of the original function to figure out the domain and range of the inverse. So in summary, remember that given the points on the graph of a function, you can find points on the graph of its inverse using the relation xy becomes yx. That's because a function can be reflected over the line y equals x to find its inverse. This relationship tells us that the domain of the original function becomes the range of the inverse, and that the range of the original function becomes the domain of the inverse.